All right, hopefully you made it through the homework for section P4. Now we're on P5. So it's almost maybe seems a little frustrating when you hear about it, but this section, we're going to try to learn how to do the opposite of what we did in the last section. In the last section, a big part of it was taking polynomials like 3x minus 2 multiplied by x squared plus 5x plus 1, something like that, and multiply it out, right? Okay, I'm going to do this times this and this time, et cetera, et cetera. So we're going to learn the opposite of that, factoring polynomials. This is, let's see, writing a polynomial as the product of smaller polynomials. The product of smaller polynomials. And remember, product means two things that multiply together. So let me see, if I multiply this out, what would I get? 3x cubed plus 15x squared plus 3x minus 2x squared minus 10x minus 2. See, once you do this a lot, you get good at it, or it goes quickly. So then we got, just trying to get the answer here so we can imagine what we're trying to do in this section. Okay, so in this section, going this direction from to the product to the answer, that was P4, the section P4 in this book. Now P5 is the opposite. What if you were given this thing and you wanted to remember, or you wanted to go find out what were those two polynomials that were multiplied to make this big polynomial? That's what we got to learn in this section. And I know that sounds crazy. Why did we learn one process when we just want to undo it with another process? Well, in some situations, it behooves us to do it one way, and sometimes we need to do it the other way. It just depends what our objective is. Back in chapter 4 or chapter 3, chapter 4, and on in this class, sometimes we need to factor, sometimes we need to multiply. It depends what we're trying to do, the overall big picture here. So that's what we're trying to learn how to do. The bad thing is, depending on the polynomial you're given, there are a lot of different ways you could factor. So there's this type of factoring out the greatest common factor of a polynomial. We're going to talk about that first. These are just the names of the different factoring techniques. Don't worry about how to do them. That's what we're going to learn. Factor by grouping. So there's so far 2 factoring techniques. Factoring trinomials. There's a 3rd factoring technique. Factoring the difference of squares. Don't worry if that doesn't sound familiar because we haven't even talked about it yet. Factoring perfect square trinomials. Okay, there's even another one. Factoring the sum or difference of 2 cubes. Oh my gosh, there's another one. Anyway, and then a general strategy for factoring, that's like if you were just given a polynomial, how would you even know which technique to use out of all these techniques and blah, 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 blah. So that's what we're doing today. This, I would say, is one of the most important review topics that is in algebra. It's hard to master, so maybe I'll try to give you lots of practice and maybe some extra credit type of assignment, so you have extra practice. This is one of those things, yeah, that you only get good at it if you practice it a lot. Because this is one of those things that's hard to commit to memory unless you do it a lot. Like, I imagine like someone that's trying to go into the automotive industry, you're trying to learn how to fix cars or work on cars. You could read a book about fixing cars, but you think if you just read a book, you're going to really know how to do it? I think you have to kind of go hands-on and practice doing it, and then you get good at it. This is kind of, I know it's not similar. It's similar in that way, though, that you have to really practice it to get good at it. You can't just look at someone else do it or read it in a book. Yeah, all right. So introduction, we've kind of already said what factoring means. It's the opposite of multiplying. Factoring a polynomial expressed as the sum of monomials means finding an equivalent expression that is a product. So just, yeah, like I said, basically going from the answer we saw in problems from P4, the last section, to, yeah, the 2 or more polynomials that they looked like as a product. The goal in factoring a polynomial is to use one or more factoring techniques until each of the polynomials factors, except possibly for a monomial factor if it's prime or irreducible. In this situation, the polynomial is said to be factored completely. Okay. So that sounds like a lot, but it's kind of like, I don't know if you remember along, in some old math class, they used to say factor into primes. You take a number, like let's say 24. I didn't write that very good. Primes. And you wanted to, 24 is not prime. Prime means nothing divides into you except 1 and yourself. 24, it could be 2 times 12, right? 2 is prime because nothing divides into 2 except itself and 1. 12 is not prime though. He's 2 times 6. 2 is another, that's another 2. He's prime. 6 is not prime though. It's 2 times 3. And those are all prime. So that's that was something we did a long time ago in math. Maybe you didn't do it. We don't really need it now. It's just, this is going to be an analogy. So 24 is 2 times 2 times 2 times 3. And that's kind of 24 factored into all its prime components. It's like breaking 24 down to its tiniest building blocks, I guess. So like in some science classes, you break something down into its tiniest components, like electrons and protons and neutrons. Everything can be broken down to those little things. It's kind of like that with math. You can break any number down to prime factors. And then what we really care about today, though, is you can break any polynomial down into prime polynomials, I guess. So it's kind of akin to that. I don't know if that helps you. And don't worry if that doesn't make too much sense. I think as we do examples, it'll make more sense. But the first technique, okay, this is our first technique, greatest common factor. This is I would say this kind of helps me think of it. It's the opposite of distributing. Why are math terms always so long? But it's like, I think one of the examples we did in the previous section was you had a monomial multiplied by a polynomial, let's say, blah, I'm just making this up. This isn't the exact problem. I don't remember what it was. It was something, something like that. Yeah, sure. And then we distributed it, okay. Is that how you say distribute? Yeah, the past tense of distribute is distributed. I don't know. Anyway, 3x squared times x to the 4th, and then we got 3x squared times negative 5x squared. I'm just adding powers here. 3x squared times negative 3x would be negative 9. Powers added together, 2 plus 1 is 3. So that was, like I said, with section P4, we were starting with this, the product, and we wanted to find the answer. We were kind of undoing the factoring. But unbeknownst to us, sometimes it's good to have it factored. So if you were given this guy instead and they said factor this, that means that this could be broken down into two things multiplied together. And that's what we want to figure out how to do in this section. Figure out how do you go from a polynomial to, But this one, the first technique, greatest common factor, if you were to look at these three terms, they all have something in common. Like their coefficients, something divides into all three of those coefficients. 3, 15, 9, 3 divides into all of those. So I kind of already know that can kind of be extracted, sort of, is the word I would use. And then I've got x to the 6th, x to the 4th, x to the 3rd. They all have some x's in common, so I could extract some x's, you know? That's the idea. Just kind of look at the terms you're given in your polynomial and see what do they have in common, I guess. But don't worry about that example. That's just giving you the idea. This is factoring out the greatest common factor is the opposite of distributing. All right, so let's try this. Here's an example here. 10x to the 3rd minus 4x squared. So, and notice when they say factor out the greatest common factor, the key word is greatest. I could take, let's say I could just take an x between these two guys. I could say, well, 10x to the 3rd and 4x squared, they have an x in common. What happens if I take an x away? Well, you could do that, but it's in my best interest to take as much as I can out. So I'd say, what divides greatest divisor is something that divides in of both coefficients. If I look at the coefficients, 10 and negative 4, what's the biggest number that divides into both of those? It's kind of a letdown. It's not much. It's 2, right? I think 2 is the biggest number that divides into 10 and 4, or 10 and negative 4. So I got that. And then I want to take the smallest power of the variable, or smallest exponent of the variable, I guess. So between the two powers I saw over there, there's a 3rd power and a 2nd power. I can only take the 2nd power. Kind of like, imagine I tried to take a 3rd power. That wouldn't really work because this 2nd term only has 2 x's to spare. I can't take 3 from him because he only has 2 to spare. I think this is my greatest common factor. Greatest common factor. That's the biggest thing that the two terms I was given have in common, the 10x to the 3rd and the 4x squared. So it's like, yeah, like I said, I'm doing the opposite of distributing here. If I take 2x squared out, I would kind of, excuse me, I'm trying to kind of rebuild it. 2x squared multiplied by what would be this 10x to the 3rd? So in my mind, I kind of do it two separate things. I do 2 times what would make that 10? 2 times 5 would have to be 10. How about the powers though? I got x squared times what would make x to the third? Because I would want to be able to distribute this 2x squared onto something to get 10x to the third. And I think that's it. It's kind of like I have 2 x's here. How many more do I need to get 3? I would just need 1 more. So I think that, wait, what happened to that square? Oh my God. Oh, wow. All right. And then similarly, now I should be able to multiply this 2x squared by something over here and give me negative 4x squared. 2 multiplied by what would be negative 4? That would be negative 2. And then x squared times what would make x squared? That's all I really need right there. I think that's it. And the good thing is, this is actually my answer here. I don't know why I rewrote it. It's the same thing that was there. But the good thing is you can easily check it. Check by, we know the opposite operation to factoring is distributing or multiplying. Check by distributing. So imagine I multiply that 2x squared in here. 2 times 5 is 10. X squared times x is x to the third. And then I'll do 2x squared times negative 2. That's negative 4x squared. Is that what I started with over here? Yes. Everything matches up. Yes. So that means I did it right. But if the powers were off or the sign, the minus or plus was wrong, I probably factored wrong, or I probably pulled out the wrong greatest common factor or something. So that would be my answer. It's, yeah, like I said, it's almost like they're giving you an answer you saw in section P4, and now your job is to give them the original problem almost. Yeah, anyway, that's a weird one. And now this one's even weirder. This one's trying to build us up to the next factoring technique. This one looks weird, but between this term and this term, what do they have in common? It seems like you can't do this, but in this case you can. They both have this little factor of x minus 7 in common. Notice it's common to both of them. So even though it seems weird, I can take that away from both of them. The greatest common factor between them is that whole x minus 7, which seems like you can't do that, but they're multiplied by it. It's 2x times that thing and then 3 times that thing, so should work. And if I factor it out, what's left here, I guess? Okay, I would say, and when you factor out the greatest common factor and then you start thinking about what goes inside the second parentheses, you should have a space inside the second parentheses for every original term. This term needs to have a space and this term needs to have a space. Then I just ask myself, kind of reverse engineering, x minus 7 times what makes this term? X minus 7 times, well, the only thing it's missing is that 2x. And then similarly, x minus 7 times what would make this term? Well, the only thing I'm missing is the 3. So it's kind of like the leftovers go in the second parentheses. This 2x and the 3, they go here and here. But it looks weird, but that's our answer. That looks, yeah. What do you mean you don't have to write it with the weird circles around the 2x and the 3? 2x plus 3. Excuse me, but if you were to distribute this x minus 7, boom, boom, it would be x minus 7 times 2x plus x minus 7 times 3. And that's technically the same as the original. I think we mentioned before, if you're multiplying two things, you can switch their order. 2x on the right side, 2x on the left side, doesn't matter. I could write 2x on the left, 2x on the right. Same thing with this 3. Since he's being multiplied by this x minus 7, it could be switched to the other side. And that's the same as the original, so I know I did it right. It's a weird one. Maybe just to be safe, I hope you don't mind. If you want, you can kind of fast forward this video and if you get it and move on. But I'm going to throw in another extra example just for funsies. How about factor out the greatest common factor of something with more terms, because each of those only had 2 terms. How about 8x to the, how about y? Let's go crazy with a y instead of an x. That's crazy. X to the 5th, or sorry, y to the 5th minus 24 y to the 3rd plus 45. No, we don't want to do that. 44. That's nuts. Y squared. Yes, just crazy enough to be interesting. Just like my favorite people. Just crazy enough to be interesting. All right. There we go. Now there's 3 terms. 1, 2, 3. and I focus on one thing at a time. I'd say, okay, let me see. What do their coefficients have in common? What's the biggest number that divides into 8 and 24 and 44? I think 4, right? Because 8 could divide into 8, 8 could divide into 24, but it cannot divide into 44. I think 4 is the biggest number that divides into all three of those numbers. So I got that part down. And then I should be able to take some number of variables, but like we kind of mentioned up here, you have to take the smallest power you see. I see a 5th power, a 3rd power, and a 2nd power. I can't take more than 2 because this last term, he only has 2 to spare. I can't take more than 2. He doesn't even have more than 2. So that's as much as I can take out. Okay. And then like I mentioned before, I'm going to have a space for all the original terms inside the parentheses. So this guy, he's going to have a little representative in here for him. Maybe I'll color code these things. I love color. Why is it so fun? And then this second term is going to have a little representative here for him. Isn't that cute? And what about another guy? I'm running out of, wait for it. Wait for it. My obsession with color is messing everybody up. I'm sorry. Oh, good. Pink. So awesome. Yeah, look at that. All right, anyway. All right, everybody has a representative inside the parentheses. That's very good. I just have to kind of, like I said, reverse engineer it. 4y to the 2nd power times what would be this first term, 8y to the 5th power. So I could focus on one thing at a time. How about coefficient-wise? 4 times what makes 8? 4 times 2 would be 8. How about the y's? I would just say, I have 2 y's. How many more y's would I have to add to it to give me 5? 2 plus what is 5? That would be 3. There we go. All right, now this guy's all taken care of. Don't worry about him anymore. How about you, my friend? 24. You look like a good term. 4 multiplied by what would make negative 24? Negative 8? Wait, what the hell? 6. What the heck? Oh, that should take my job away. I don't know how to multiply. 4 times 6 is 24, right? Yes. All right, and I have 2 y's here. How many more y's would I need to put here to make 3? I only need 1 more, really, so that's perfect. Y squared times y would make the y to the 3rd that I want. All right, looks good. Last one. Now I would like to multiply this outer guy, this greatest common factor, 4y squared times something to give me this last pink term. 4 times what would make 44? That would be 11. And then y squared, I have 2 y's. I actually only want 2 y's, so I don't want to add any more y's. I think that's it, just 11. So that would actually be my answer. That's it. And yeah, you can always check by distributing. Take that 4y to the 2nd power and distribute it into the parentheses. Multiply it in and make sure you get what they gave you to start with. Make sure this is what you get. If it's not right, then maybe check to make sure either your greatest common factor is wrong or maybe one of these inner terms is wrong and it's actually not multiplying to make what you think it's multiplying to. So hopefully that makes sense. It takes some practice for sure. It definitely takes practice and then you get good at it. All right, so the second technique, that was the first technique. If you ever see a polynomial and all the terms have something in common, either they all have the same variable or all their coefficients have a divisor, the same divisor, then you should do that first technique where they have the greatest common factor taken out. But if that doesn't work, then here's another technique, factor by grouping. Some polynomials have only a greatest common factor of 1. However, by a suitable grouping of the terms, it still may be possible to factor. This process is called factor by grouping. And I think we're going to mention it later, but this technique uses this. How do you spell technique? Technique? Why does that look wrong? I don't know. You know what I'm trying to say. Use this technique when given 4 terms. So if your polynomial has 1 term, 2 terms, 3 terms, 5 terms, you cannot use factor by grouping. It's only for 4 terms, not a monomial, not a binomial, not a trinomial, not 5 terms. But notice these guys both of them have 4 terms. So let's try this. Okay, it's really weird, but even though there's no setup, they don't explain how to do it. Let's maybe put some steps here. First one is focus on the first and second terms. Factor out their greatest common factor. So like in this first example here, the left one, I always have to draw, I know it's sad, but I have to draw this kind of barrier. I want to look at the third and the fourth terms because they're just sitting right there. But don't make eye contact with them, okay? Pretend they're not there. Between the first and the second terms, what do they have in common? They don't really, their coefficients have no common divisors. 4 and 3, nothing divides into them except 1. So that's nothing interesting, but they both have at least x squared in common. I can take that out, the smallest of the powers. So it's kind of like, imagine just the first two terms, do a problem like in the previous where you factor out the greatest common factor. Okay, if I take x squared out, x squared times what makes 4x to the third? I need the 4 and one more x to give me 3 x's. I think that would work. X squared times 4x, yeah, that would work. Then how about x squared times what would give me negative 3x squared? I think I only need the negative 3. And that would work. And you could do a kind of quick check. If I distribute that x squared in, boom, boom, would I get these two terms? I think I would. All right. Now what I do is now I ignore the first and the second term and do the same thing to the third and the fourth terms. Now, factor out the GCF, or greatest common factor of the third and fourth terms. Feel free to write these steps, you could pause this video or whatever and write these steps on here if you think you'll forget later. Or these videos are always, you can watch them anytime, so you can always look at it again if you don't want to write it down now. So now I'm trying not to look at the first and the second terms. I'm focusing on these two guys, 12x and 9. I definitely can't factor any x's out because the 9 doesn't even have an x to spare. But 3 divides into both of those, right? Positive 3. I think that's about it. Okay. So I've got the GCF, and then similarly, I have to kind of do this reverse engineering. 3 times what would make 12x? That would be 4x. And then 3 times what would be negative 9? I would need negative 3. All right. And then at this point, it should be, if this is actually factorable, sometimes the original problem it can't be factored. But if this is factorable, what's in parentheses will be the same. Factor, now you need to factor the GCF. Why am I writing it down here? I should be writing it here. Oh my gosh. Factor out the GCF, greatest common factor of the remaining two terms. Because you kind of took a 4-term polynomial and made it 2. It looks similar to that second problem we did above, that example that had parentheses, kind of weird. It's like this is one big term and this is one big term, and they happen to have this 4x minus 3 in common. If those are not exactly the same, we're lucky in this one. It's 4x minus 3, 4x minus 3. If those are not the same, that probably means this whole problem can't factor. But I don't think they would do that to you in the homework. So I'm going to factor that out, 4x minus 3. I take it away from this first big old term, and I take it away from the second big old term. And then pretty much whatever's left over from each of those terms goes in the second parentheses. Because I would say, okay, 4x minus 3 times what would give me this first big term? The only thing I'm missing is the x squared. So he's going to go here. And then also, similarly, 4x minus 3 times what would be 3 times 4x minus 3? You just need the plus 3. And that's it. That looks weird, but that's I think that's one of the hardest things to me in factoring, is just like trying to remember, what am I even trying to do and why is that a good answer? I want to make a polynomial that's kind of spread out, just a bunch of terms. I want to make it look like a product, or two smaller polynomials multiplied together. That's my goal, and that's what I did. I took a polynomial that was degree 3 because it has a power of 3 with 4 terms, and I made it a product of two binomials with lower powers. And that'll help us in the future solve equations. Believe it or not, this actually helps you. It's hard to believe, right? Yeah, I think to me, this technique, factor by grouping, is the weirdest one. And I think it has, for me, the steepest learning curve. It just seems like, what? I can't, especially this step from here to here. It's like, I can't, can I do that? Yep, I guess you could do that. Sometimes some things seem illegal, but they're not illegal. At least in math, okay? Not in real life. Now, how about this second one? This looks like a good one. Boom, boom, boom. I'm gonna try to do the same thing. Go back to the first, what do you call it? The first step. Focus on the first and second terms. All right. So it's really sad, but I have to do this. I have to like create a barrier, because I'm gonna try to look at that negative 2z and the negative 10. Don't even make eye contact with them because they'll distract you. I'm gonna look at z to the third and 5z squared. Okay. Their coefficients have no common factor or common divisor, but I can definitely take some z's out. The smallest power between them is a 2. I can take 2 out. And then like before, I'm going to need a space inside the parentheses for each original term. Z squared times what would make z to the third? I need one more z to get to that first z to the third, okay? And then z squared times what would make 5z squared? I would need a plus 5. And then you can do, usually at this point, I quickly check. In my mind, I'm gonna distribute the z squared in. Z squared times z is z to the third, check. Z squared times 5 is 5z squared. Okay, check, check. So far, so good. Now I ignore the first and the second terms, and I'm gonna move on to the third and the fourth. Between these two guys, negative 2z and negative 10, what do they have in common? I guess I could take a 2 out. 2 divided into 2, 2 divides into 10. This is a very subtle note to remember. I'm going to write it down. Note. Factor out the middle sign along with the second greatest common factor. So at this point, I factored a 2 out, but what really needs to happen to make this whole thing work is this sign right in the middle of the problem between the second and the third term. That has to be the same sign as what your second GCF here, and that's what I'm working on. So I can't just factor a 2 out. I have to factor a negative 2 out. Otherwise, what's in parentheses here will not be the same as what's in parentheses here, and we cannot proceed with the problem. So in the last one, we didn't really have to worry about it because the sign was a plus. And I already had a plus. I didn't really think about it, but I did copy the sign without even thinking. So it's only really something I have to really worry about or think about when the middle sign is a minus, because I might not think to take a minus out. So yeah, if you ever get stuck, and if these are not the same, that's probably the problem. If the parentheses, you know what's in parentheses, are not the same. See this note, because that might mean you forgot to focus on the sign of between the second and the third terms. Oh my gosh, there's so much to remember. I feel like I should be apologizing for all this, even though I didn't make it up, but I'm so sorry about this, you guys. All right, then a little of that. Negative 2 times what would make negative 2z, because that's what I'm trying to make happen here, z. Negative 2 times z, yeah, okay. And then negative 2 times what would be negative 10? Well, 2 times 5 is 10. Would it be plus or minus 5? If I made it a minus, it would be a negative 2 times a negative 5, which is a positive 10. That's not what I want. I don't want a positive. So I actually have to put a plus here for it to be a negative times a positive and make a negative. So that, and then at this point, I'm not quite done, but I'm going to make a good quick little check here. What's in parentheses is the same, z plus 5, z plus 5. That means you've done everything right so far. You're kind of halfway there and you're doing it right. If those are not the same, that means someone either gave you a problem that's not even factorable, which I don't think would happen in this class, or you did something wrong, so we got to think about it. Now I can factor that thing in, that parentheses they have in common, z plus 5, factor that out, and then the leftovers go in the other parentheses. Z plus 5 is taken out of both of them. Then who's left over from the first parentheses? Z squared, and then from the second parentheses, the minus 2. So I'm going to put those in their own little special parentheses over here. Boom. And that's it. I'd say that's the weirdest factoring technique of all, and probably the least used, maybe, of all. I'd venture to say that's probably true. So it's good to learn, though. Unfortunately, factoring comes back for the rest of your math life. Even in calculus, you're going to need factoring. People are not happy about it. Okay. Anyway, next factoring technique, a third one. All right. So these ones, trinomials. So the first thing we did was polynomials that have a common factor. We know what to do with that. But now what if you have, and then the second thing we did was factor by grouping. That was for 4 terms. Now it's trinomials. So 3 terms. If you see 3 terms, the unfortunate thing is if you see a trinomial with 3 terms, there are 2 different techniques that could possibly be applicable. One of them is easy and one of them is difficult. And the difference is if the leading coefficient is 1 or not. If A equals 1, the leading coefficient, then the problem's not so bad and pretty easy. We'll figure that out. And then if it's not one, we'll see what to do in that. That's almost its own technique. But right now we're just going to focus on if the leading coefficient is 1. Because that's the easier one. Okay. This is what we need to do. All right. Okay. Let's say this is our general trinomial, ax squared plus bx plus c. Actually, it kind of helps to have an actual concrete example. This is kind of describing what to do, but it's kind of nice to have an actual example. For me, that's math is hard to understand if I don't see actual numbers. It's like this is an English class, not a math class over here with all these ABCs. I'm gonna make one up. Okay, x squared plus 6x plus 8 or something like that. Okay, so that's a trinomial, and the leading coefficient is 1. Notice that there's no number in front of x squared, so that means it's automatically a 1. These guys, they're always going to factor into 2 binomials. That's a good thing, like this, and it's always going to be an x and an x. The only question is, that's always the setup. Every time you have a binomial with no coefficient in front of x squared, just a 1, it's always this setup, and then your job is to figure out these 2 numbers. It's going to be x plus something or x minus something, but they're going to be 2 numbers. These numbers, whatever they are, add up to this middle term, 6. B is 6, because here they're calling the middle term bx. B. In this example, it's 6, but other examples, it could be something else. They add up to that, but multiply to 8, which is C. Oh, dang it, I didn't write 8, I wrote 6. Okay, so that's the key, and I think those 2 stipulations, they have to add up to this and multiply to that. It should be only one combination will work. So usually, I think if this is kind of new and you're not used to it, the good thing to do would be, okay, they have to multiply to 8. So what kind of numbers multiply to 8? 1 and 8. Multiply to 8. How about 2 and 4 multiply to 8? But also you can be negative, which is a bummer. You can have -1 and -8, because they multiply to make 8. And -2 and -4 multiply to 8. So that's kind of the idea that these are all my possibilities. It could be 1 and 8. It could be 2 and 4, because those multiply to 8. It could be -1 times -8, because those multiply to 8. And then lastly, I think the last option, -2 and -4, those multiply to 8. You have 4 options, but there's only one pair of those that add up to 6. That's the determining factor. So they have to add up to 6. All right, do 1 and 8 add up to 6? 1 plus 8, no, that's not 6. So this is the wrong pair. I don't want that. How about these guys? Is 2 plus 4, 6? Ooh, that's a winner, I think. Yeah, okay. Just to be safe, I'm going to rule these guys out. -1 plus -8. That's definitely not 6 like we want. It has to add up to 6. How about -2 plus -4? It's -6, not 6. So yeah, these won't work. That won't work. The only pair that has product 8 and add up to or sum 6 is 2 and 4. So it'd be a 2 and a 4, or it doesn't really matter what order they're in. It could be 4 first and 2 second. Either way would work. So that's the idea. And the good thing is you can always check your answer by multiplying it out. So that would be, let's see. Once you get good at this, I think you won't need to check your answer. But if you think, okay, I don't feel too comfortable with this, I better check. I can always multiply it out. I'll go x times x. Okay, that's x squared. And then x times 2 is 2x. 4 times x is 4x. 4 times 2 is 8. Now I got some like terms here. X squared plus, now 2x and 4x make 6x. All right, and that is the original problem, right? It was x squared plus 6x plus 8. Okay, check, check. I must have done it right. This is the answer. So it sounds complicated, but the more of these you do, the better you get at them. So if you want, you can pause the video and write that down or whatever, but I put a few examples down here, quite a few actually, because they don't take long to do. It's just thinking of the numbers is the hard part. So right away, all 4 of these problems right here, I can kind of set them up. So this first one, all 4 of these examples, they're all 4 trinomials. They all have 3 terms, and their leading coefficient is a 1. The thing in front of x squared or y squared is 1. So I know that they're going to be set up the same way. Binomial with the x, binomial with the x. I'll think about the answer later. This guy, same thing. Binomial with the x, binomial with the x, binomial with the x, binomial with the x. That sounds like some lyrics to a song or something. And then this last one, almost the same thing, except it's a y, but whatever. Y's don't scare me, geez. All right, that's the setup for all of them. I just gotta, each of them has a unique pair of numbers that I need to determine here. So on this one, it helps, you know what helps me is to always remember there's a plus in the middle term and a little multiplication symbol on the last term. So I need two numbers whose product is 40, or they multiply to 40 and add up to 13. So this is in my head. You don't have to write this down, of course, but this is what I'm thinking. Which two numbers multiply to 40 and add up to 13? There are a lot of pairs of numbers that multiply to make 40, but there's only one unique pair of those that would add up to 13. So, you know, you can start thinking about it, and if you know the answer, boom, you just write the numbers in the parentheses with the x right here. But I can always start brainstorming. What about 1 and 40? 1 times 40 is 40, but 1 plus 40 is definitely not 13, so no, that's not it. 2 times 20 is 40. With 2 and 20 add up to 13? Nah. What else goes? 4 times 10. 4 times 10 is 40, but 4 plus 10 is not 13. Close though, huh? Close. All right. What about 5 and 8? 5 times 8 is 40. Ooh, and 5 plus 8 is 13. That's a winner. Yeah, the answer is 5 and 8, because 5 times 8 is 40. That's what I wanted. And 5 plus 8 is 13. I think any other pair of numbers either wouldn't multiply to 40 or they wouldn't add up to 13. There's only one unique pair of numbers that do both of those things. Those are the ones, 5 and 8. I have to put a plus or a minus. If they're negative, of course, put a minus. But if they're positive, you have to put a plus. Oh, I put the same number twice. Come on. And then, like I mentioned on the last example, I put the 5 on the left and the 8 on the right. But if you put the 8 on the right and the 5 on the left, it doesn't matter. There's the same answer and they're both right. So whichever one you like, you don't have to write both. It's not like on the midterm or something. If you don't write both answers, I'm going to mark you down. One or the other is definitely sufficient. So, and that seems like a lot. I know in that example, I wrote a lot down. There was a lot of kind of brainstorming, but to be honest with you, all that is actually happening in my head as I do these problems. Just writing it down might explain it better to people that have never seen it before. That's all. So you'll get so good at this, you'll just look at it for 2 seconds and boom, write the answer. And all this will just be happening in your head. So anyway, similarly on the second one over here, let's see. I want two numbers that add up to the middle term's coefficient and multiply to this guy. But that helps me to remember because I think it's easy to mix them up. You think, I think, wait, they have to multiply to which one and add up to which one. But the plus goes to the middle guy and the multiplication goes to the last guy. So I want a pair, I want to find this, a pair of numbers whose product, or that multiply to make product, is that last term, -12. And what does that mean? That means that one of these numbers I'm looking for has to be negative and one has to be positive. The only way you're going to multiply two numbers and get a negative is if they have opposite signs. So that might help me think about these numbers. And sum is -1 because that's the coefficient in the middle. So usually, yeah, like I said, I think it's better to start with their product one. Okay, they have to multiply to -12. What kind of options do we have here? How about -1 multiplied by 12? Would that work? -1 plus 12 is 11. Oh, why did I put in the parentheses there? -1 plus 12 is not what I want. They add up to 11. I don't want them to add up to 11. I want them to add up to -1. So that's not going to work. Does not equal -1. Okay, what else? What two numbers can multiply to -12? How about -2 times 6? Because that would make -12, but -2 plus 6, that's not -1 like I want. How about -3 times 4? That would be 12, but -3 plus 4, ooh, it's not -1, but it's +1. So maybe if I switch the negative onto the other guy, maybe instead of making it -3 times 4, what if I make it 3 times -4? Because 3 times -4 would be -12. And now when I add those together, I'll get -1 like I want. Yeah, that's a winner. So and all that can be happening in your head. This list of numbers that I just wrote, you don't have to write that out. You're just kind of brainstorming, but if it helps, that's good. So I think the answer is 3 and -4, because yeah, 3 times -4 is -12. 3 plus -4 is -1. So that looks fine. That's a good answer. Or you could switch them. Just if you switch the 4 to the left side and the 3 to the right side, you have to carry the sign with it. The 3 is positive and the 4 is negative. So that, yeah, that's it. Like, yeah, again, if you like, this is on a midterm, if this one of these problems is on our midterm, let's say, and you don't show any work for these problems, you just show me the answer, then that's fine. I imagine once you get good at this, all this scratch work is happening in your head. That's fine. How about the next one? Let's see. We got, well, doesn't matter what order we go in, I guess, but this next one here, y. All right, it's a y. We already got the y's down. Now I want two numbers that multiply to make -63 and add up to 2. So I always think 63. First of all, the number they have to multiply to, that's going to be the kind of the revealing factor. I know one, this seems like a silly one. 1 times 63 is 63, but I want it to be negative. I don't think there's any way I can make either of those negative, 1 or 63, and have them add up to 2. They're too far apart. What about 3 times 21? I know that makes 63, but I think there's no way that I can make 3 or 21 negative and add up to 2. They're too far apart again. How about 9 times 7? That could work, I think, right? Because those are 2 apart. 9 and 7 are 2 apart. If I make 9 negative, that's not going to work, because although -9 times 7 is -63, like I want, they add up to -2, but I want them to be +2, so I think I gave the wrong guy the negative. Not you, sir, it's you. You were the one all along. 7. So I think that's it. 9 and -7. Yeah, and then I usually do a quick check. Is 9 times -7 really -63? Yes, yes. If I add them, do I really get 2? 9 and -7. Yeah. Okay, looks good. Or you could have done it the other way with this, the -7 on the left and the +9 on the right. Doesn't matter what order they're in. Yeah, but I think it's almost like, I don't know, almost like when when you learn your multiplication tables, you memorize 8 times 9 is this and 7 times 8 is this. This is kind of similar. I think the more you do this, the quicker these numbers will come to you as you're thinking about these things. What numbers multiply to make this and add up to this? The numbers will just start coming to you quickly, and yeah, you won't even be trying to come up with them. Like I said, on my deathbed, I'm going to remember how to do this, but I won't remember my grandkids' names. It's not like I want it to be like that, okay? That's just the way it's going to be. Let's see. Ooh, this is a good one. Let's see. Okay. I want numbers that multiply to make 15, but add up to 7. Okay. Look at 15. What times what is? The good thing is those are both positive numbers. +15, +7. So I think all my numbers I need are going to be positive. 1 times 15 makes 15, but there's no way that's going to add up. 1 plus 15 is not 7. So what else? 2, no. 2 can't go into 15. Does 3 go into 15? 5 times. Yeah, but 3 plus 5 is not 7, so that's not going to work. That might be actually all my options. That's it. 15 is just, right? Yeah, 1 times 15 or 3 times 5. I think that this means since there is no pair of numbers whose product, or in other words, that multiply to, whose product is 15, and whose sum, in other words, adding, I should say, plus, product means multiply, is 7. So this polynomial, the one that we were given, is prime. In other words, cannot be factored. Cannot be factored. That's it. So that's we haven't seen that yet, but there are some times where you see a polynomial like this one. It's a trinomial. Okay, I know what technique to use. Boom, and I try to do it. Doesn't work. That means it's prime. You cannot factor it. You won't see that too often, but I wanted to throw one of those in there. So if you're doing homework and they happen to throw a prime one in there, I don't want you spending an hour trying to factor something that can't be factored. That seems kind of messed up, right? It's like if I told someone, hey, go find a unicorn, and they go out in the forest and they don't come back for a month. That's messed up. Of course they're not going to find one. Send you on a wild goose chase finding something that doesn't exist. That's so wrong. Good times. Okay. This is probably okay. The bad news. Is this our 5th technique? No, 4th technique. Technique number 4. This is the hardest technique of all, if I'm being honest with you. It's hard to master. It takes a long time, but if you master it, oh my gosh, you're gonna feel good. You probably should get a little like badge that says I kick ass at math or something. Yeah. But you know, what are you gonna do? It's okay. We got this. This is the one you need to practice a lot and then you get good at it. Okay. This is for factoring a trinomial with leading coefficient that's not 1. So we already know what to do with the ones that they're a trinomial with a coefficient of 1. We saw that in the previous examples. But now what if it's not a 1? Like in this one here, we got this is a good example to start with. 3x squared. Sorry, it's kind of blurry. Plus 16x plus 5. If only this 3 were not here. He ruined everything. If that 3 were not there, I could factor this the old-fashioned way, like in the third technique we saw above, but nope. Anyway, all right. My first step is to, sorry, this is so blurry again, write the trinomial in standard form. It should already be in standard form. Remember, that means just all the like terms are already combined, and it's from highest power to lowest power, left to right. It's already like that, so okay, we're good. Check, check. Now we're going to multiply the first and the third coefficient. So the first one, I think they label it as A usually. A is 3, B is 16, C is 5. You multiply A times C. This sounds kind of random, but it's going to actually do something later, I promise. The first and the third coefficients, A times C, and then you put it, a lot of people like to use this little X. It's just, there's going to be a lot of numbers running around in this technique, and it's just kind of nice to have a place to gather your thoughts, I guess. So sometimes people call this the X method. Sometimes people call it the diamond method. Maybe because when I made this little diamond, it made a diamond. Yeah, that's what it says. Use diamond. Okay. So I put A times C, or the first and the third coefficients. I multiply them together and put it here. And now, let's see. I want to write the number from step 2 on the top. So that number I found, 3 times 5 is 15. I wrote that at the top of the diamond. And now I'm going to write the middle coefficient on the bottom. Because we use the A is 3 and C is 5. We multiplied those to make this number. And now the middle coefficient, the one we haven't looked at yet, 16, he's just going to go down here as is. He doesn't need to multiply by anybody. He's good as he is. Okay. All right. So far, so good. It's just memorizing what to do. Put this number there, multiply that by that. Okay, now step 4 is missing, but this is where it gets good. Okay, you guys, this is like the joke. This is going to be the punchline of the joke. Find 2 numbers. It's going to be very similar to the last technique at this point, whose product is A times C. So that number up there, 15 in this case, in this example, I'm going to put a little product sign so I remember. I want to find 2 numbers whose product is that and whose sum, or in other words, they add up to the other number, 16. So I'm going to put a plus there so I don't forget. But notice that the original problem I was given, this 3x squared, what is it? 3x squared plus 16x plus 5. I think if I looked at that, I don't know if I would remember what I'm trying to do. I'm not trying to find 2 numbers whose product is 5 and whose sum is 16. I'm looking for 2 numbers whose product is 15 and whose sum is 16. So that's why it's kind of nice to have this little diamond or X thing to put your ideas and thoughts in. So 15, I have to think about what 2 things multiply to 15. I got 1 times 15, 3 times 5. That might be about it. But I want the pair that add up to 16. 3 plus 5 is not 16. But 1 plus 5 is 16. Those must be the ones I want. Okay. So those are the guys. Find 2 numbers whose product is A times C. Write them in the remainder of the diamond, I guess. The remainder of the diamond. By that I just mean there's 2 spots open in that diamond. You might as well just throw them in there. Is that a weird thing to say? So like, okay, those 2 numbers I just found, 1 and 5, or sorry, 1 and 15, I'm gonna put them here. Just so I have all my numbers that are, if I was doing all this all in my head, it might be too much and my brain would explode. Too many numbers running around, I need places to put them. All right, there they are. And now this part is kind of the weird part to remember, but it's okay, it's gonna be okay. So now that I've written those there, and this sounds, the way I'm gonna write this sounds funny, but once we do it, hopefully it'll make more sense. I'm gonna now rewrite the trinomial breaking the middle term into two terms whose coefficients are the numbers found in step 4. Yeah, step 4. That sounds crazy. I think that it's not hard to do it in math. It's hard to write that. So what I'm going to do is take the trinomial that I was given. I'm going to rewrite it. Okay, oh wait, what the heck? 3x squared. The middle term I'm going to change though. So 3x squared, the first term stays the same. The plus 5, he stays the same. But like it said that we wrote, the part that we wrote out, I'm breaking this middle term. It was 16x, but now I'm going to rewrite it as two terms whose coefficients are the numbers I just found. So those, what were they, 15 and 1? Well, and it doesn't matter what order they're in. I wrote 1 on the left, 15 on the right, but this whole process would work the same if you wrote the 15 on the left and the 1 on the right. All right, so I'm going to put the 1, it's plus 1x, just match the same coefficient, and then 15x. So it's kind of, it almost looks like I just made my problem more complicated. I took 16x and wrote it as 1x plus 15x, which is true, right? 1x and 15x do add up to 16. I've broken it down. But what I've done is I've kind of designed this trinomial. Now it's a polynomial with 4 terms. And now I should have set it up, if I did everything right so far, this should factor by grouping. Remember that grouping method we did where we break it down the middle and we factor out the greatest common factor and yada yada. So that's kind of what we did. I took a trinomial that I don't know how to factor, made it a polynomial with 4 terms that I do know how to factor, I guess, is because that's factor by grouping. All right, that's it. Whew. And this sounds crazy, but we're going to do a few examples. And yeah, this one for sure, this technique, the more times you try it, the better you get. And the less you'll have to write out and the quicker that you'll think of the right numbers and all that. Yeah. Anyway, oh my gosh. Yeah, it's a lot. That's a lot. All right. So now I'm going to factor by grouping. Remember what we did was I look at the first 2 terms only. I'm going to forget the third and the fourth terms are even there. Between the first and the second terms, what they have in common is an x. If I take an x out, 3x plus 1 would be left. And if I check distributing that x, I think that does give me the first and second terms. And I have to carry this sign with me. Okay, this plus needs to come down. Between 15x and 5, I can take a 5 out. If I take 5 out, 3x plus 1 is left because 5 times 3x would be 15x, 5 times 1 would be 5. And at this point, if you did everything right so far, what's in parentheses should be the same. If these two things are not the same, this 3x plus 1, 3x plus 1, or whatever the case may be, then probably you got the wrong numbers, those pink numbers that I highlighted in pink. Something went wrong above. You want to go check your work, but I think we did it right. So just like in factor by grouping, I'm going to take that common thing out, that 3x plus 1, which we highlighted in yellow. And then in the second parentheses is just going to be the leftover stuff that we factored out initially, the x and the 5. Those will go here. And that's your answer. Phew, and you can always check. It almost seems like, honestly, it seems like witchcraft. Like, what? There's no way that's how you, there's no way. But if you multiply this out, you can always check. Multiply to check. Just do kind of foil it out. First times first, outer times outer, blah, blah, blah. And it will be the original guy that da. So yeah, that's a lot. Okay, so take a moment if you need to. For me, I probably have to stare at the wall for a little while because I don't know. In a different class I taught, there was some similar type of problem where it was like, we did something and everybody's mind was blown. And I said, guys, what do you think? Does that make sense? Or do you have any questions? And everyone was silent except one person said, I think while you were doing that example, my soul left my body. For some reason that made me laugh so hard. I don't think that he meant that in a good way though. But I feel like that in this, almost like my soul says, I'm out of here, dude. You could sit here and watch this, but I can't be here. So I'm gonna try that again. I know we can't see the steps right now, but I think you can always refer back to them. We're gonna do this 2 more times to hopefully get a good feel for it. The more times you do it though, the easier it'll get. They'll be like second nature. I'm gonna do the whole x thing. It's okay. We're supposed to do a times c, the first term, or sorry, the first coefficient of 3 times the last coefficient, -4. A times c, 3 times -4. Make sure you do the negative too. Keep the sign. Would be -12. And then the middle coefficient, in this case, it's a 1, because that's the coefficient of x. B is 1. All right, I write those there. A times C on the top, B on the bottom. And then it's hard to even remember which one are they supposed to multiply to and which one are they supposed to add to. Multiply to the A times C and add up to 1. If I start thinking about what are pairs of numbers that multiply to 12 but add up to 1. Like I think like we mentioned before, if you already know the answers, then don't worry about, brainstorming it. But I always think, what times what makes 12? 1 times 12, of course. Is there any way I can make either 1 or 12 negative or both negative and have them add up to 1? I don't think so, right? Okay, moving on. 2 times 6. What if I make 1 or both of those negative? There's no way they're going to add up to 1. They're too far apart. In order for two numbers to add up to 1, one would have to be negative, one would have to be positive, but also they'd have to only be right next to each other, like 2 and 3 or 7 and 8, something like that. 3 times 4 is 12. That might work, right? I need to make one of them negative. In order for them to add up to a positive one, the bigger one has to be positive. Okay, so I better make the smaller one negative. Does that work? Negative 3 times 4 is negative 12. Check. Negative 3 plus 4 is 1. Yeah, those are the ones. Okay. And feel free not to write any of that down if you don't want to. Whatever helps you. So I think those will work. Those are my guys. And if you put those in the opposite order, if you did 4 on the left and negative 3 on the right, same thing in that X thing, that's fine. The whole process might look different, but the answer will be the same. So I think we found our numbers, negative 3 and 4. All right, now we need to rewrite our trinomial. I'm going to rewrite. The first term is going to stay the same. The last term stays the same. But the middle term is going to break into two terms, the coefficients of which are going to be those numbers I just found, negative 3 and 4. But I'm just going to copy the variable that the middle term had. He had an x. There we go, plus. All right. So maybe I'm going to kind of highlight those so we see where they came from. All that stuff I wrote off to the left with that diamond thing and the lower rectangle that has a 12 and all that, none of that really matters. They were only a way to get these two numbers. Now that I have these two numbers, I don't care about any of that stuff anymore. Now I'm just factor by grouping. So really any of this stuff over here on the left, if you don't need to write that down, don't worry. The main thing is you need to find these two numbers and then you're good to go. I can go erase all this stuff if I wanted to. That was the hard part. Now factor by grouping. I'm going to break this down the middle and then do like we did before. Let's see, I'm going to take between the first and the second terms, I can take a 3x out, I think. 3x times x would give me the first term. 3x times negative 1 would give me that second term, I think. Excuse me. Between the third and the fourth term, I can take a 4 out, but it has to be positive. Remember we said whatever the middle sign is has to stay. So if that was a plus, this is going to be a plus. If I take 4 out, 4 times x would give me the first term. 4 times negative 1 would give me that second term. Okay. I think that looks good. Now, looks like this is where I cross my fingers and say, did I do everything right so far? Oh my God, please help me to. Oh yes, thank God. That means if I see these things in parentheses are the same, I did everything right so far. Oh my gosh, thank God. So I could factor that out. X minus 1 comes out of both of those big old terms, x minus 1. And with all the just the leftovers that were factored out, the two little greatest common factors are going to go in the second parentheses, 3x and 4. There we go. And then we're done. 3x plus 4. There we go. So that's it, those two. And I think I mentioned earlier that if I wrote the negative 3 at this point on the left and the 4 on the right. If you were to have switched those, you put the 4x on the left and the negative 3 on the right, this process might look different, but eventually you get the right answer. You would get 3x plus 4 and then x plus 1, but that's the same thing. So, x minus 1. Yeah. So it really doesn't matter what order you put your two special numbers in. It doesn't matter. Because in the end, those are the same thing. Yeah. So also keep that in mind if like you're comparing answers with a friend or a classmate or something. If they get this and you get this, don't think you're wrong or they're wrong. It's the same thing. It doesn't matter what order the factors are in. Yeah, and you can always check your answer by FOILing or multiplying it out. 3x times x, 3x times 1, 4x times blah, 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 All right, let's do this one more time. I know this is like, we don't want to do this, but it's something we need to do. Kind of like when my kids, I get them to eat their vegetables. It's like, I know, nobody wants to do this. Okay, you guys, you got to do it though. It's good for you. That's kind of like this. I don't want to do a third example. I'm sure you guys don't want to listen to me do one, but it's good for us, I guess. I don't know. A is 5, B is -9, and C is -2. That kind of helps me to think about that too. On the top, I'm going to put A times C. A was 5, C was -2. 5 times -2 is -10. Okay, good stuff. And now I've got my middle term is -9. Oh yeah, that goes down here. I had a brain fart for a second, just like, what? What was it supposed to do with that? All right, so I want to find two numbers that multiply to make -10 and add up to -9. And if you already, some people I noticed, they're just gifted and they think of the numbers right away. It's boom and boom. Man, if you already know the answer, then you count yourself lucky and just proceed with the problem. But if not, then you can come down here and think about it. Okay. What two numbers multiply to make 10? It could be 1 times 10. Maybe one of those is negative, or two of those, both are negative. I don't know. 2 and 5. But which pair might add up to -9? I think 2 and 5, there's no way those are going to add up to -9. Even if you make both of them negative, they only add up to -7. So it's got to be these two somehow. Which one do I make negative? I guess if I want the two numbers to add up to a negative, the bigger one better be negative, right? So I think I need -10 and 1. Would that be good? 1 times -10 would be -10 like I want. Okay, check. 1 plus -10 is, yeah, that's the one. 1 plus -10 is -9. Yep. So I think those are the ones we want. I'm going to put, just because I happen to write the 1 on the left and the 10 on the right, that's how I'm going to write it here, but you could always switch those. You put the -10 on the left and the 1 on the right. Your answer is going to be correct no matter how you do it. All right, now I'm going to rewrite the first term. You stay the same, sir. Last term stays the same, but this middle guy is going to split up. It was -9x, but now I'm going to write those numbers that I found with the x. Okay. It was a 1 and a, +1 and -10. Those were the guys I found. Okay. There they are. And yeah, like I said, at this point, I've been really leaning on all that work I did on the right, all this writing, all this diamond and all this work down here. But now that I've written this part, I can let go of all this. This is like, you're useless to me now. Good luck in life. Oh, it all disappeared. So I guess that really cemented it. As long as I got the right numbers, then I don't need those anymore. All right. Now I'm going to split it down the middle and factor by grouping. Between the first and the second term, only an x is in common. If I take x out, x times what is 5x squared? Okay, that would be 5x. X times what is 1x? I guess just 1, right? And now between the third and the fourth term, let's see. Between 10x and 2, I can take a 2 out. But I got to remember that whatever that sign was in front, the middle sign, I've got to keep it. So not just a 2 has to come out, but a -2. Otherwise, what's in parentheses here and here won't be the same. Let's see, -2 times what would be -10x. I would need 5x, right? Yeah, -2 times 5x. And then -2 times what is -2? I guess 1? Yeah. All right. And this is where I've crossed my fingers and say, oh God, I hope this is the same as this. Oh, phew. If those are not the same thing, then yeah, I would say check your work above. Maybe this is that would be why you shouldn't erase this stuff if you wrote it down, because there might be some salvageable stuff in there to check your answer and stuff. But luckily we got the right thing so far. 5x plus 1 can be taken out. That's what's in common between these two terms. And then the leftovers are going to go in the second parentheses, the x in the front of this guy and the -2 in front of that guy. There we go. That's the answer. Or yeah, like I mentioned before, if you had switched these two terms, if you wrote -10x on the left and +1x on the right, your process from there to the end would look different, and your answer would look like this: x plus 2, 5x plus 1. But that's the same exact thing. Just, yeah, you arrived at the answer in a different way, but it's the right answer. So whatever. Oh my gosh. So those for sure take practice, and feel like, as you do these problems, it's fine to look back at this and kind of follow along. Look at one of these examples and then say, okay, what did we do first? That's right, we did this. And then do it on your example, and then look back at this video or whatever and say, okay, what was the second thing we did? Yeah, there's nothing wrong with that, because this one, that was the hardest technique of all. That was the fourth technique. Now it's easy peasy. Don't worry about the rest of these. Easy peasy. So this is the fifth technique. Oh my gosh. That's why I think most students' most hated thing in algebra is factoring. It's just because depending on what you're given, there's 7 different things you could have to do. But the good news is methods 5, 6, and 7 are all for binomials. We haven't really talked about binomials yet. I think we did factor out the greatest common factor, which works for any size polynomial. And then factor by grouping was for 4 terms. And then we had 2 techniques for the trinomials, depending on if their leading coefficient was 1 or not. Now, the last 3 techniques are all for binomials, and they're pretty simple, I want to venture to say. Okay. Let's see, now what? This is our first technique. This actually looks pretty similar, maybe, because we saw this formula backwards in section P4. But I think we said it the opposite way. We were trying to multiply. I think they said, well, you know, if you ever see a binomial multiplied by itself, but the signs are opposites, you have a plus and a minus, then it's just going to be the first term squared minus the last term squared. Now we're doing the opposite thing. If you ever see something like x squared minus 4, we're trying to go backwards. I see something squared minus something. It's going to factor into 2 binomials, one with the plus, one with the minus. And all you have to do is say, all right, what was squared to make the first term? What can you square and give me x squared? That would be an x. And then 4 is what squared? That would be 2 squared. There's a 2 here and a 2 here. Boom. That's it. So that's kind of the formula. If you're given something, a binomial with a minus in between, that looks like a square and a square. It'll always factor into plus, minus, and then what did you square to give me that first term? Put it here and here. What did you square to give me that second term? Put it here and here. Boom, like that. So it's, and that looks kind of crazy, but when you see the examples, it'll make more sense. It's so simple compared to that last method. It's like, you probably don't even believe me. Like, okay, there's got to be more to it than that. No, there is not more to it. It's amazing. All right. So this is the difference. That's what they call these types of difference. I know it said it on the previous page. Difference, the reason they say difference is because it's a minus in between. Difference means subtract squares. And that's because they're 2 things squared. Something to a power minus something to a power, you know? Yeah. So those are definitely squares. This is a square. And this is a square, 4 squared, z squared. So you really have something like this. And like we mentioned on the previous page, it always factors into 2 binomials, one with the plus, one with the minus. The first term, and each binomial is going to be the same. It's whatever was squared to make that first term, z and z. And then the second term is whatever was squared to make the second term. In this case, 16 is 4 times 4, and that's it. That's your answer. Boom. Or you could do it the other way, z, the minus on the left and the plus on the right. Yeah, it doesn't matter what order the terms are in. As long as the factors are the same. That's it. Isn't that nice? So even though that previous method was so long and confusing, at least it's good to know that it balances out with these easier ones. And here's another one. This one's harder to tell, but this first term, that's 6x squared, because 6 squared is 36. Of course, x squared is x squared. And then 25 is 5 squared. This is going to factor into, similarly, a binomial with a plus, a binomial with a minus. And then the first term of each one is going to be whatever was being squared to give you the first term. In this case, 6x is going to go in the first place for both. And then whatever was being squared to give you the second term is going to go in the second place, 5. Easy peasy. Or you could put the minus on the left and the plus on the right if you wanted to. If you're trying to be contrary. That's it. That's nice, right? I love it. All right, now when I tell you that one's used pretty often, all through calculus and beyond, you'll see that a lot. And so I think because it's sprinkled in every math class you take, it'll be hard to forget. That one's hard to forget. These ones are easy to forget. So this is the last 2 techniques. This is like technique 5 and technique 6. Wait, did I mix them up? 6 and 7, huh? Last 2 techniques, thank God. There are already enough as it is. We don't need any more than that. But these are also for binomials. So this you're starting out with something that looks like this. So I guess an example would be like, let's see, x to the 3rd plus 8. Because those are both things to the 3rd power. X to the 3rd is obviously something to the 3rd power. But 8 is 2 to the 3rd power, 2 times 2 times 2. So it factors into, it's like this kind of a complicated formula. It almost looks like the difference of squares, but it's way more complicated. Yeah, but I would not make you memorize this. Don't bother memorizing this. I mean, if you want to, you can. I'm gonna say, I don't want to say don't memorize. You can. I'm not gonna tell you, don't you dare. You don't need to memorize either of these. They're either gonna be on your midterms for you, like, okay, you need to use this formula, so here it is, or they won't be on the midterm at all. So that's, yeah, I don't want you to feel like you have to memorize that stuff. All right. So the one thing to point out here is there is a technique for the sum of cubes, and there's a technique for the difference of cubes. So notice that's kind of interesting. There's the sum of cubes, so there's a plus, and the difference of cubes is a minus, but there's only a formula for the difference of two squares. There is no formula for the sum of two squares. So that might be something to point out here. Let's see. No. Okay, actually, I'm gonna just put it here. Note. Sum of squares cannot be factored. So something like x squared plus 4, that's prime. It cannot be factored. There's no way. But x squared minus 4, that's the difference of squares. That was the fifth technique we had. We know how to do that. And then we know how to factor the sum or the difference of cubes. If it's the third powers, either way, plus or minus, it can be factored. Yeah. So there's that example right there. Boom. I'm just going to go for it. I'm going to write the formulas up here so they're in our view. And the first one has a minus, so I'm going to need that minus one. It's a minus b times a squared plus ab plus b squared. So really, if you had this formula in front of you, which, like I said, if it's on the midterm, it's going to be there. Your job is just identify what a and b are. A is what you have to be squared. Or sorry, what you have to be cubed to give you the first term. Of course, that would be x. B is what you have to cube to give you the second term, and that would be 2. So you're just filling in this formula. I'm just going to rewrite this formula, a minus b, but leave the a and b out. A minus b times a squared plus a times b plus b squared. And I'm going to fill in every a from that formula with x, and every b from that formula with 2. There were a's here, here, and here. That's here, here, and here, but I'm going to replace a with x, because in my particular example, I have an x. X, x, x. Okay, and now the b, because b is just like a placeholder for whatever was being cubed to give you that the second term in the binomial. I actually have 2, so wherever there was a b in the formula, here, here, and here, I'm going to put a 2. And that's really all there is to this process, except maybe simplifying. So 2 goes here, 2 goes here, 2 goes here. That means that this binomial is just x minus 2, x squared plus, I can clean this up a little bit. Usually when you see an x times a 2, you don't write x2, you write 2x. And then 2 squared, 2 times 2 is 4. And that's it. So as long as you know how to use the formula, it's fairly easy, I think. Since I'm not, I'm not asking you to memorize anything. And then this one looks like it's not a difference of cubes because it's not a minus, it's a plus. So we're going to use the sum of cubes formula. A cubed plus b cubed equals a plus b times a squared minus ab plus b squared. Notice the formulas are almost the same. The only difference is where the minus is. The top formula, this is a minus and this is a plus. But then for the sum of cubes, you just switch those two. Now it's a plus and a minus. So it's almost the same formula, but it's not quite the same formula. All right, this guy, I'm going to kind of, this is a separate example, so I'm going to separate it. I'm going to write kind of the skeleton of this formula. It's something plus something, so blah plus blah. And the second parentheses, it's a term minus another term plus another term. The first one's squared. The second one's two things multiplied together. The last one's a square. Okay. I just now have to identify A and B, and then we're good to go. Easy peasy. A is what's being raised to the third power to give you this first term. 125 is what to the third power? I think it's 5. 5 times 5 times 5 is 125. And then B is what are you raising to the third power to give you 64 y to the third? It's definitely something y. At first I want to say 8 because 8 squared is 64, but I don't want to know what raised to the second power is 64. I want to know what raised to the third power is 64. That's the guy. 4 to the third power is 64. Okay, wherever there was an A in the formula, I'm going to put a 5 because in this specific example, A is 5. There was an A there, an A there, and an A there. I'm gonna replace them with 5s. Okay, 5, you go there, dude, and you go there, my friend, and right there. And then wherever there was a B, I'm gonna put what? 4y, that's right, 4y. There was a B, 4y going there, also there, and also there. And I think we got this. The simplifying is the last step. So 4y, you're replacing B in the formula, 4y, 4y. All right, time to simplify now. 5 plus 4y, looks good. And now I'm squaring 5. 5 times 5 is 25, okay. Minus, now I got 5 times 4y, that's 20y, plus 4y squared is 4. Oh, sorry, whoops. I should have put this in parentheses. Whew. Because you're not just squaring the y, you're squaring the entirety of 4y squared. So it's really 4 squared y squared. Not that I had to write all that, but you know, 5 plus 4y times 25 minus 20y plus 4 squared is 16y squared. That was a close one. So keep that in mind. You're not just squaring the variable. If there's a variable attached to a number, you have to square that number as well. Oh, no, this is the hard part. Oh my gosh. What is this? There we go. And this is the general factoring technique, okay? That's, if there are 3, oh yeah. All right, so it's just saying, first, if there's a common factor, factor it out. If there's not, then we move on. From here, we count the number of terms. If there are 4 terms, we use factor by grouping. If there's 3 terms, it's a trinomial. You have to do the factoring technique of a trinomial, etc. So I'm just going to go for it. All right. The first one, I say, is there a common, actually, that's the first thing you should think of first. Is there a greatest common factor? Because if there is, your life will get a lot easier once you take care of that. I think of these 4 problems on this page, only the first one has a greatest common factor between 3x to the third, 30x squared, and 75x. What's the most I could take out? 3 goes into all those coefficients, I think, and they all have at least an x in common. If I 3x times what would be this guy, x squared. 3x times what is 30x, would be, or sorry, 30x squared, negative 10x. 3 times what is, or sorry, 3x times what is 75x, that's 25. So that was the greatest common factor, but check this out. This is crazy. I can do another factoring technique on this, because although the 3x in the front can't really be worked on, this is a trinomial with leading coefficient 1, so it should be that easy factoring technique. I just put an x and an x, and then I say, what 2 numbers multiply to make 25, but add up to negative 10? I think that would be negative 5 and negative 5, right? Negative 5 times negative 5 is negative or positive 25, check, check. Excuse me, and they add up to negative 10, that's it. But I want to say, you notice those 2 factors are the same, x minus 5, x minus 5. In the homework, I think they're going to want you to write that as that thing squared. So keep that in mind. If you end up factoring and you're done, look at what you factored. If you have 2 of the same factor like this, x minus 5, x minus 5, when it's the same factor, then you're going to be expected to kind of make it look nicer and simplify it by writing that thing squared. Phew, so that was tricky. Okay. Let's move on to the second one. Looking at the second one, there's only 2 terms. Is there a common factor between them? No, there is not. So I write GCF. In this case, no, there's no GCF. So now I count the terms. Count the terms. And then as we went along in these 7 techniques, we talked about which of them had 2 terms, which had 3 terms. Now this has 2 terms. This particular one in example 7b, 2 terms. So it's got to be, if it factors, sometimes they don't factor, it's got to be one of 3 options. It's either the sum of, or sorry, dang it, I should say sum of cubes, difference of cubes, or the difference of squares, because we said there is no technique for sum of squares. Sum of squares cannot be factored. So one thing I can say is this a couple cubes or is it a couple squares? 64 is a tricky guy because he is something squared and he's also something cubed. 64 is 8 to the 2nd power. He's also 4 to the 3rd power. So he's not going to help us. 64, thanks a lot. What about you, p to the 3rd? You are a 3rd power, so you're a cube. That means it can't be this one. It can't be difference of squares because that's not a square. 64, he fit the bill, but not the cube. So, okay, it's got to be one of these. Is it sum of cubes or difference of cubes? There's a minus between them, so it's difference of cubes. Aha, okay. So now we know which technique to use, And then this is the one where it's just a formula, easy peasy. It's supposed to be a cubed minus b cubed. Looks like a minus b times a squared plus ab plus b squared. And I just have to identify what's a and what's b in this particular problem here. A is the thing you're cubing to make the first term, so just p, lowercase p. And that's another thing. I think in the homework, they're going to get mad if you, like, that's a lowercase p. If you type uppercase p when you put the answer in, they're going to say it's wrong, so be careful. Lowercase b, be careful, as this is what you're cubing or raising to the third power to get 64. That's 4. So I just need to rewrite this whole formula with a replaced with lowercase p and b replaced with 4. It looks like this, plus a times b plus b squared. All right, a was p. So I'm going to put it here. That's where it goes in the formula. A. All right. There's a p going to be going there. P here, p there. And then we got the letter b is 4. So he's going to be replacing b in this formula. All 3 places that he happens. Here. All right. 4 was going to go there. 4. All right, and then all that's left is kind of to simplify that. Usually this binomial doesn't simplify, p minus 4. Here I've got p squared plus p times 4. Usually you write that as 4p, not p4. And then we got 4 squared is 16. And that's it. That's beautiful. And this trinomial here, it will never factor. So if you're looking at them and you're thinking, I wonder if that factors further, like this one over here did. For some reason, it's honestly, it's unbeknownst to me. I don't know why. But those guys never factor any further. I think because they don't fit any technique type of thing. I don't know. Don't worry about it. Once you do difference of cubes factoring, you're all done. Now, how about we'll look at 7c? Kind of wrote on him. Sorry, it's kind of hard to look at, but that's okay. Oh, there you go. Look at that. Beautiful. Is there a greatest common factor here on this part 7c? It almost looks like it. There's all the terms seem like they have a y, but that last guy doesn't have a y. And the coefficients have no, there's no divisor that divides into them, so there's no greatest common factor. I should check every time, but no, there's not in this case. Now I'm going to count the terms. And that should tell me what technique to use. There are 4 terms. Good thing there's only one factoring technique that uses 4 terms. 4 means factor by grouping. So actually, factor by grouping might be the best technique because it's only one option. If it's a trinomial, 3 terms, it's it could be one of 2 techniques. If it's a binomial, there could be one of 3 techniques. But if it's 4 terms, boom, you know exactly what to do. If this doesn't work, there's nothing I can do. So I'm going to break it down the middle. What do the first and the second term have in common? Y to the third. If I take y to the third out, what's left? I would need a y minus 4 in order for that y cubed to distribute to make that first and second term. All right, between the third and the fourth term, I can factor a 9 out. I have to keep that sign, of course. 9 times what would give me 9y minus 36? I think I need y minus 4 there. All right. Now if I take that y, and they're the same, that's a good sign. Y minus 4 is the same here and here. I'll take that out, and then whatever's left over, the dark blue stuff, y to the third here, plus 9. There we go. That's it. All right. Phew. Now the last one, here we go. This is a binomial. It has 2 terms, so it's one of 3 techniques. It's gonna be well, we can just look at the ones from part B. It's either sum of cubes, difference of cubes, or difference of squares. Somehow that got erased. It's almost like a tricky one because this is a 4th power. That's not a 2nd power or a 3rd power. But it's tricky because I can make that look like a 2nd power if I'm feeling crazy. X to the 4th is x squared. What? And 81 is 9 squared. This, in disguise, this is a difference of squares. All right, where a is x squared and b is 9. So remember then you can always look back at the formula, but for difference of squares, it was if it's something squared minus something squared, you can write it as 2 binomials, one with a plus, one with a minus, and it's just a in the first place and b in the second place. So it should look like something with a plus, something with a minus. And then the first thing is just like, okay, well, what did you square to get the first term? It was x squared, so he's gonna go here and here. So might as well put it there now, x squared. And then the second term is, what did you square to give the second term? This guy is gonna go here, here. What squared made 81? It was 9. There we go. So that's a good answer, except this is a crazy trick. This is like a trick problem. One of these factors again. This here, this is a sum of cubes, which is prime. Prime. Because it's the sum, or sorry, not cubes, sum of squares. Come on. Because it's a square. So this is a second power. 9 is something to the second power. But this is a difference of squares again. What? So I could use this formula again on, at least on this part. Because x squared minus 9, what squared gives you x squared? It would be x and x. And then what squared gives you 9, 3, and 3. So it's almost like cover up, imagine that this wasn't here for a second. Just look at this guy, x squared minus 9. If you were given a problem like that, you'd say, oh, that's a difference of squares. Okay, that means it's a plus and a minus. What can you square and get x squared? It's an x. What can you square and get 9? It's a 3. Boom. But there happened to be more to it than that, so I just carry that part down. So that's kind of the tricky thing. Even once you master factoring techniques, you have to keep factoring, keep kind of like, once you factor once, look at each factor and see if you can factor it more. Do any factoring techniques apply to each of those factors? This one it happened to be. This one's a tricky one because this one was tricky because x to the 4th is x squared squared, and 81 is 3 squared squared. So it's kind of like, because each of those is a square twice, it could be broken down twice, sort of. That's a tricky one. All right, anyway, that's the end of that. So this, I know it's very overwhelming, and I'm sorry if you feel kind of like, yeah, overwhelmed, and I don't know what the right word is, but just keep practicing and it'll get easier, I promise. And I think everybody forgets factoring too. So if you forgot or you forget in the next month, then don't worry, that's normal. You got this.